let's take a look at an example. So as always, I would encourage you all to set up the problem and try to work through it by yourselves before coming back to the video for the solution. So in this example, we have a unity feedback system which has the following open loop transfer function. So g of s is equal to, in the numerator, 10 times the quantity of s plus 20 times the quantity of s plus 30, and in the denominator we have s times s plus 25 times the quantity of s plus 35. And so what we want to do is find the steady state error for three inputs, so 15 u of t, 15 t u of t, and 15 t squared u of t. And so we notice that our three inputs correspond to our three common test inputs. So we have a step input, we have a ramp input, and we have a parabolic input. So in each of these three cases, we also notice that we do not have unit inputs. So for instance, we don't have our unit step input, but instead we have a gain of 15. Similarly, for our ramp input, we don't have a unit ramp, but we have a gain of 15. For our parabolic input, it's a little bit trickier because remember, we said we had 1/2 t squared was our unit parabolic input. So what that means here is that we have a gain of 30 because we have 30 over 2, which is giving us this 15 out front. So we have to consider that as we're plugging into our equations. So talking about equations, we sort of have two basic approaches. We can either go to our general equation for the unity feedback system, and so that's what I'm going to show here. No particular reason, it's just sort of less error if we're going back to that general equation each time, less room for error, but it's perfectly fine if you want to go to those specific equations for a step input. So for step input, we would go to an equation from the step input video. For our ramp input, we go to that equation, and then for our parabolic input, we go to that equation. Of course, we're going to get the same result regardless of which method we use. So let's go ahead and take a look at that. And one other thing I do want to note before we do that is before we even start talking about our steady state error, what we need to do is we need to check our system stability. And so as I said in the first video of this unit, for this example, we're not going to go through the process of doing that. We're just going to say the system's stable, otherwise we wouldn't be looking at it. But in reality, what you're going to have to do is check that system stability first. And so practically what that means in terms of this system is, of course, we'd have to find our overall equivalent transfer function, t of s, incorporating that unity feedback, and then we'd create a Routh table or check the poles via some other means of our denominator. Okay, so assuming our system is stable, we can then move on to our first input. So let's say for our first input, we have r of t is equal to 15 u of t. So what we get then is an r of s, which is equal to 15 divided by s. And so again, we can see our gain of 15 coming in here. So as I said, I'm going to go back to our general equation, which is going to be e of infinity, so our steady state error, is equal to the limit as s goes to 0 of s times our r of s, so in this case 15 over s, divided by 1 plus g of s. So our s's here cancel out, and because we have a constant in the numerator and our 1 here is a constant, we can take that limit down to our g of s, so we get 15 over 1 plus the limit as s goes to 0 of g of s. And so what we notice is that this equation here is the equation that we had for a step input. I've just adjusted the numerator to account for our gain of 15. So we could have come directly there using that more specific equation for a step input. All right, so now what we do is we can let our s go to 0. We take that limit, and so what we see is that we let all of these s's go to 0, and because we have this s here, that limit is ultimately going to be equal to infinity. So let me go ahead and remove those. So we say that this is going to be equal to 15 divided by 1 plus infinity, so that's going to give us 0. And so before we move on to the next one, we can kind of say we should be able to expect roughly what type of error we're going to see for each of these inputs, because if we take a closer look at this g of s equation here, we can see that our n, which we had in our general equation, is equal to 1 in this case. So for a step input, if we have n equals to 1, we said that should correspond to a 0 steady state error, which is what we see here. So sort of thinking ahead, we know that for a ramp input, for n equals 1, we should have some finite steady state error. And for a parabolic input with n equals 1, we should see an infinite steady state error. So let's go ahead and work through that problem and confirm that those two things are true. So first, let's consider our ramp input. So now we have r of t is equal to 15t times u of t. And so that means our r of s is equal to 15 over s squared. Again, I need to keep track of that gain term, that 15. So we have e of infinity, our steady state error. Again, I'm going to go back to our general equation, is limit as s goes to 0 of s times 15 over s squared. Our s cancels out with that. And so let me finish filling in our denominator. So we have 1 plus g of s. And so again, we have that s. So let me make that a little clearer so that only cancels out with the squared. So we have that remaining s multiplying through our denominator. So we end up with 15 divided by the limit as s goes to 0 of s times g of s. And again, this form here is what we had from our ramp input to a unity feedback system. So we could have just come directly there as well. Now we need to evaluate that limit of s equals 0, or limit as s goes to 0 of sg of s. So let me just copy that and pull this down here. And so we can say that this is going to be equal to, so the s out front here is going to cancel out with this s here. So we're going to get rid of that one. And now we're going to have these four s's go to 0, which means we're left with 10 times 20 times 30 in the numerator and 25 times 35 in the denominator. So as expected, we're going to get some finite number. So we have 10, 20, 30 divided by 25 times 35. So if we plug that in, we get that that is approximately 6.857. But remember, that's not what we're looking for. We need to plug that in for this limit up here. So we get this as approximately 15 divided by that 6.857, which we see is about 2.1875. And so I think that's actually exactly equal to that if we use a stored value. So as expected, for n equals to 1, with a ramp input, we get some finite steady state error. Okay, so moving on to our last input, which was our 15t squared u of t. So now we have r of t is equal to 15t squared u of t. And so remember, we said that's equal to 30 times 1/2 t squared u of t. And the reason I want to do that is because this was our unit parabola here. So we can say that that gives us an r of s, which is equal to 30 over s cubed. So our e infinity, our steady state error, so e of infinity rather, as t goes to infinity, is equal to the limit as s goes to 0 of s times our r of s, which is 30 over s cubed, divided by 1 plus g of s. So again, I've gone back to the general form. That cancels out with one of those. We now have an s squared being multiplied by our denominator. So we have 30 over the limit as s goes to 0 of s squared g of s. And again, we recognize this as the form for a parabolic input to our unity feedback system. So what we see now is with this s squared out front, one of those s's is going to cancel out with this s here. However, we're still left with an s in the numerator. So that remaining s in the numerator means as we take this limit as s goes to 0, that whole term in the denominator is going to be 0. So we end up with 30 over 0, which is going to be infinity. So as expected for our parabolic input, we have an infinite steady state error. And again, keep in mind that's based on our initial g of s we were able to say n equals 1, so then we kind of knew generally what to expect, either 0 steady state error for a step input, finite steady state error for a ramp input, and infinite steady state error for a parabolic input. So if you want to work through some additional examples to get some practice with this, you can look at the examples on pages 278 and 279 in the 8th edition textbook and get a little more practice with these equations for the various input types for our unity feedback systems.